The ORAN, Service Management and Orchestration Platform, or simply SMO platform, is an intelligent automation platform which applies automation at scale to simplify the complexity of networks, as well as improve network performance, enhance customer experience, and minimize RAN operational costs. In this video, we explore the SMO architecture, internal components, and how it can benefit today's and tomorrow's RAN operations. Here, we are talking of RAN operations, because SMO is responsible for RAN domain management and orchestration. Let's start with what is SMO. The SMO is an automation platform for Open RAN radio resources. When we say automation platform, it is designed to manage the life cycle of the RAN functions and applications. But the challenge is how to make SMO and its components as interoperable in this global world of wireless industry. And that's where the ORAN Alliance comes into the picture, and so, the specifications for SMO framework are being defined by the Open RAN Alliance to make sure the interoperability of SMO components and interfaces. And the SMO is designed to be open by creating an automation platform based on cloud-native principles that deploys RAN functions and applications over open interfaces. Now, let's look at the internal components of the SMO and their respective functionalities. First component is NFO. NFO stands for Network Function Orchestrator. Next is FOCOM, which stands for Federated Cloud Orchestration and Management. Next is OAM, which stands for Operations and Maintenance. Next is non-RT-RIC, which stands for Non-Real-Time RAN Intelligence Controller. And, apart from these, there are few other components, like Slice Management Function for RAN, Inventory and Topology Management Function. There are few other components too, but these are the major components. Let's check each component in more details. We will start with NFO. The NFO is responsible for the orchestration of the cloud resources. To understand NFO functionality into details, let's first have a quick look at the cloud and the O2 interface between SMO and cloud. cloud consists of multiple deployment management services or DMS and single infrastructure management service or simply IMS. DMS manages network functions or applications, whereas IMS manages infrastructure-related management from cloud perspective. As that's where the O2 interface also divided into O2 DMS and O2 IMS interface. And the NFO uses this O2 DMS interface for the management of the network functions, for example, the initial deployment of the network functions, and any subsequent lifecycle management actions necessary on the respective CNF or VNF instances, such as healing, updates, scaling, software upgrades, and the termination of the network functions. Now, let's look at one example use case of NFO. Assume, goal is to scale out the network function deployment. Means deploying another NF deployment unit. Here, shown is the example sequence diagram to achieve this goal. If one can see here, NFO makes an API request to the DMS component over the O2 interfaces for the NF scale-out, and the DMS responds back with the confirmation, again on the O2 interface. This was one simple example of the NFO functionality. Likewise, there are multiple another use cases. Now, let's move to the next component of the SMO, which is FOCOM. Like NFO was taking care of network function orchestration and management, here FOCOM takes care of cloud resource orchestration and management over the O2 IMS interface. The FOCOM is responsible for accounting and asset management of the resources in the cloud. Here are the main capabilities of FOCOM towards cloud. Maintaining the cloud infrastructure data in the SMO inventory. Monitoring the infrastructure. Provisioning the infrastructure, for example creation of cloud instance, installation of cloud layer. Infrastructure software management. And complete infrastructure lifecycle management. For example, a very simple use case. If a new cloud instance is to be created, then FOCOM will initiate that process by talking to IMS over the O2 IMS interface. Let's discuss the next component of SMO, which is OAM. OAM here stands for Operations and Maintenance, and this is responsible for FCAP's management of O-RAN managed entities. The O1 OAM interface includes implementation of fault, configuration, accounting, performance, security functions, file management and software management functions for O-RAN network functions. OAM has majorly three components, which are performance management, fault management, configuration management. RAN NF Performance Assurance Management Service. It provides RAN NF performance data, like network KPIs, obtained by consuming O1 interface and Open Front Hall M plane interface. RAN NF Fault Supervision Management SMO Service. It provides RAN NF fault data, like alarms, collected by O1 interface and Open Front Hall M plane interface. RAN NF Provisioning, or Configuration Management. It provides RAN NF modification services, like Day 1 or Day 2 configuration of network functions. Let's look at the previous example of NF scale-out. Here NF did its own task of deploying a new unit of network function. But to make that network function fully operational, OAM would do the configuration of that network function, placing it into network traffic. Non-real-time RAN Intelligent Controller, or simply non-RT-RIC, is the functionality internal to the SMO in O-RAN architecture. The primary goal of non-RT-RIC is to support intelligent RAN optimization by providing policy-based guidance and enrichment information to the near RT-RIC function so that the RAN can optimized. It can also perform intelligent radio resource management function in non-real-time interval, in the range of 1 second. Other RAN optimization operations are traffic steering, energy optimization, radio performance optimization, resource management, and many others. The non-RT-RIC is comprised of two sub-functions. One is non-RT-RIC framework and the another is RApps. Non-RT-RIC framework platform, which includes the platform capabilities, such as AI and ML models, communication bus, A1 termination towards the near RT-RIC, service discovery and management, and few others. On the other side, non-RT-RIC applications, or simply the RApps, are the modular applications that leverage the functionality exposed by the non-RT-RIC framework to perform RAN optimization and other functions. In simple words, RApps are the optimization algorithms that can come from same or different vendors and services exposed to RApps via the R1 interface, which enable multiple such RApps to talk to single platform. And the non-RT-RIC framework is responsible for exposing all required functionality to the RApp via this R1 interface. Now, let's look at network slice function in the SMO. Network slicing is conceived to be an end-to-end feature that includes the core network, the transport network, and the RAN. Although 3GPP has started defining network slicing support with Release 15, and in order to be compliant to the 3GPP, O-RAN has captured network slicing function in the SMO for RAN domain as slice subnet management function. And this O-RAN slice subnet management is in line with 3GPP slice management framework. In case of O-RAN, SMO slice function takes care of network slice subnet management for RAN domain. For this purpose, use cases such as slice subnet creation, activation, modification, deactivation, termination, configuration and feasibility check are considered for O-RAN architecture. Next topic is topology exposure and inventory management function. For the SMO to perform efficient operations and maintenance of O-RAN components, and to enable a global view of the O-RAN resources, it is important to maintain an inventory of O-RAN resources. Additionally, visualization and optimization of the network rely upon knowing and maintaining the relationship between O-RAN resources, for example, which network function is deployed on which cloud, which server, and is part of which network slice. Having this top-to-bottom relationship data stored in the inventory for various use cases like root cause analysis, correlation, closed-loop use cases, and much more. In this video, we covered what is SMO, its architecture, and components. Thanks for watching.